Okay, very good. So Earth system ensembles for weather and climate. I want to talk about 4 main topics and then give you some closing remarks. So first of all, Earth system models, why do we need them? Second question that I want to address is ensembles, why do we need them? Third one is ensembles of Earth system models, how should we design them? And then I want to touch on the use of Earth system ensembles in climate studies, in particular on some applications, some work that I was involved when I was at the European Center, and then some closing remarks. So Earth system models. Let me just give a brief summary of how we are doing the solving the weather problem and why this will be needed to understand why we need ensembles. But essentially what we're trying to do is integrate equations that come from physics, that describe how the atmosphere, and not only the atmosphere, different parts of the Earth system, relevant components of your system evolve so that we can make predictions. Here in particular, I wanted to highlight these 3 terms underlined by yellow, which is the tendency so how much the state variables, wind, temperature, humidity, change due to physical processes. This is actually where a lot of efforts and a lot of resources are put by scientists, by operational center, in trying to simulate at best physical processes so that we can really compute how the state variables change depending on the processes happening in the atmosphere. These equations are solved numerically on a finite grid. As we all know, for example, the grid of the European Center model includes about 10 to the 9 grid points. The spacing of the grid points is now about 10 kilometers, 9 kilometers for the European Center high resolution system, 18 for the ensemble, with a spacing in the vertical of about 500 meters. So at European Center, it's 137 levels in the vertical, 91 for the ensemble. So essentially the equation that I showed you here are solved numerically on a finite mesh. And the definition of a mesh, the resolution clearly matters a lot. And you can clearly see it in this diagram where I'm showing how you would see a tropical storm if you had simulated it, or if you had actually smoothed it and averaged it on grids with different size. That corresponds actually to the resolution of the models used at the European Center from 1981 to 2019. So if we start from 1981, the resolution at that time, one of the first resolutions used by European Center was about 210 kilometers. As you can see, if you average this image, which is a simulated satellite image from the European Center high resolution system, down to 210 kilometers, you hardly see the structure of a tropical cyclone. 85 European Center model went up in resolution to 125 kilometers, and then subsequently, more or less every 5 years, resolution was increased by almost a factor of 2 to get to the current one. So the point I want to make here is that clearly if you don't have enough resolution, if your mesh is too coarse, it's very hard to simulate fast processes and small scale processes. So resolution matters. Problem is that if you want to use a very high resolution, you need to have a very powerful computer, because the more grid points you have, the more computations you need to do to simulate the atmosphere. Now, I want to make another point about resolution, which is even if you're running now with a 9 kilometer resolution, so the grid spacing, the spacing between these points is 9 kilometers, you're not actually resolving the scales in an accurate and realistic way up to that resolution. What you see here from Nils Vedi European Center are a plot of energy spectra, kinetic energy spectra of a very high resolution SNWF simulation and of simulations done at low resolution. The TCO 1279, the red curve, is the curve that corresponds to the current operational model of the European Center. What you want to do is to be as close as possible to this black line. If you are close, if you are overlying, if your curve overlies up to this curve, it means that you have more or less the same, you're able to simulate in a realistic way all the scales up to that point. And you can see that even with a 9-kilometer model, you can only simulate scales up to about 40 kilometers. So there is about a factor of 5 between the grid spacing and what I would call the actual resolution, the resolution that your model is capable to resolve. It's interesting to compare this red curve with a curve done with another type of grid that European Center was using up to 5 years ago, a linear grid. As you can see, a linear grid even with a much larger number of spectral components has an even worse kinetic energy than the current one. Okay, but this fact, the fact that the actual resolution is about a factor of 5 or with a grid space is something we need to keep in mind when we think that, okay, now we have a model running at 9 kilometers so we can resolve scales up to 9 kilometers. This is not actually true. I think we could say that we can resolve scales only up to a multiple of a delta x, which has been estimated to be, say, between 4 and 6. Now, I said about the processes, clearly, we want to include processes in our models that are relevant for weather prediction. This is a nice graph from Dirmeyer et al. 2015, where he pointed out that the longer you want your forecast to be valid, the more components you need to include in your system. Why? Well, because if you have, for example, you simulate well land processes, there is a memory in the system coming from initial states that allow you to make predictions for longer than if you didn't have a correct simulation of land processes. The ocean can bring you in even slower scales and bring you in memories from initial state that can help you making forecasts which are more skillful than a statistical forecast based on climatology. Okay, so the inclusion of why are we including more processes in our models is because if we want to extend the scale, the validity of our forecast, and if you want to improve the simulation of our forecast, we need to have all these processes into our systems. And I'm showing here 3 examples of the impact of including coupling different components in our system. Again, the results from my former colleagues at the European Center. The first one is about the role of air-sea interaction in predicting larger scales and also in simulating the smaller scales. So I'm using this diagram, which has been modified from Hoskins' 2012 quarterly journal, where he used this type of boxes to highlight the fact that if you want to predict a certain scale in the atmosphere, like a scale with spatial and temporal characteristic xt, you need to think about how scales with a larger and slower temporal characteristics evolve, and also the interaction of a scale you're interested in with the smaller scales. This is because the atmospheric scales are not really separated, as you can see, for example, from this energy, which suggests that there is not a break in the kinetic energy spectra of the atmosphere, which means that any scale can influence the scales up and down its value. So here is, we're talking about RC fluxes. RC fluxes, so having a coupled wave model help simulate in a better way the RC interaction, fluxes of heat and momentum. And we can see it if you compare the scale of different forecasts run with or without the simulation of without the inclusion of a wave model. So if you remove a wave model, you can have a negative impact and a worse. If you remove a wave model, you have larger errors, so you are above zero, which means that your forecast of the flow close to the surface, of the atmospheric flow close to the forecast, close to the surface, gets worse. And this NWF has actually been pioneering in the coupling of an atmospheric model with an ocean wave model, work done by Anne Guillaume, Peter Janssen, and in the 1990s, and then Jean Bidreau, that I quote here later on, led to the inclusion of the coupling of the SNWF model to a wave model already in 1995. Another big step forward in the prediction of the European Center, in the accuracy of the prediction of the European Center, came from coupling the system to a dynamical ocean. So here we are talking about different type of processes, longer scale processes, but not only them. We are also talking about phenomena that are very that are influenced by the state of the sea, like tropical storms and hurricanes. So what you see here is the impact of coupling to a dynamical ocean. So this is high resolution models. If you remove a coupling to a dynamical ocean, you get a higher error in the prediction of a tropical storm, of a hurricane. Okay, this is the error in hectopascal of the intensity of a storm compared to if you run it without the tropical storm. You're talking about the forecast range of up to 10 days. Indeed, since 2016, European Center has been coupling all its forecasts to a fully dimensional, three-dimensional ocean model. The ocean model was coupled before that in the seasonal and in the monthly system, because it was clear that you needed coupling to the ocean if you wanted to do longer range predictions, as I will show you later. The third example that I want to quote is the importance of land surface processes and having an accurate description of land surface processes. Again, if you want to predict the atmospheric flow. Here I'm focusing more on the prediction of heat waves and the role of having an accurate simulation of soil moisture leads to being able to predict in a more correct way the warming that Europe experienced during the 2003 summer, when Europe was hit by one of the more intense heat waves of the past 40 years or so. So as Viterbo and Ferranti showed, you need to have an accurate simulation of the soil moisture and how the soil moisture actually changes through the forecast if you really want to make the correct forecast of intensity and the duration of this type of phenomena. I talked earlier about the ocean role. I showed you the role of a three-dimensional dynamical ocean on tropical hurricane prediction. But as I said, the coupling to the ocean came into the weather, the medium range and shorter weather prediction from people, from groups who were developing seasonal and monthly and climate models. So this is an example of the impact of coupling the CNWF model to the dynamical ocean NEMO from Frederick Vittard on the skill of predicting the Madden-Julia oscillation, which is organized convection in the tropic. So if you don't have a dynamical ocean, your curve is this blue one, which is much lower than the one we get here. And if you look at the time when you cross the 0.6 anomaly correlation line, you see that you would cross it at day 21 with a persisted sea surface temperature, and you get up to about day 28 if you had the coupled ocean. So coupling to the ocean has led to an increase in the predictability by about almost 10 days. Okay, these were results obtained looking at the very many cases. So I hope I've convinced you by showing you some examples that if you need to include in the models that are used to predict the weather, all the processes that are relevant for your prediction, and that not having them would make your forecast less accurate and would reduce the forecast kill horizon of your forecast. So then Ensemble, why do we need them? Well, if we think about the process that lead to a generation of a weather forecast, we start from observations which are used to estimate the state of the atmosphere by comparing them with our first guess of a state of the atmosphere, which is usually short-range forecast. The use of the two within complex procedures, which we refer to as data-assimilation, lead to estimation of initial conditions. Once these initial conditions are generated, we can go into forecast mode, generate our forecast, and then issue them and put them in the archive. Let me also point out that the model is clearly needed also in the data assimilation process. So it's not easy to completely decouple the role of of observation errors in the definition of initial condition from the role of a model. The model is needed to assess the state of the atmosphere in terms of state variables that I mentioned before, using observations that most of the times observe different variables than the state vectors. So you need a model to be able to translate information coming from all the observing platform that we have today to define the initial state of the system. So being able to completely discriminate between the role of observation error and the role of model error is quite tricky. So if you think about this process, you can clearly understand that if you have errors in initial condition coming from observation, or if you have error from a model, you might have a wrong forecast. So how are we doing in terms of observations? Well, for the atmosphere, we are in a pretty good state, I would say. No? Since the satellite era, we now have very many observations coming into our systems daily. Indeed, 95% of the observations used today to generate the initial conditions come from satellite. We get so many observations that we are actually not able to assimilate all of them, to use all of them in our models, because we don't have enough computer power to assimilate all of them. We don't have enough computer power to run our models at higher resolution so that we can assimilate them. This is an example of this. This is the number of this type of observation, AMPSWAY, coming from satellite of the 24th of June, 18, about 600,000 total number of ops received over a 12-hour period. Of them, only 75,000 were actually used in the data-assimilation system. What you see is that the observation has been thinned. So instead of using them at the highest density, what we have to do before using them is to average them or select one every 10 or so. And indeed, this number is about 15% of the number of the observation coming in. But there are areas that are not as well observed as the atmosphere. For example, the oceans. Now that we are coupling all our models to a three-dimensional ocean, there is clearly a need to have a very good observation also of the ocean state. And if we compare the number of ops coming of the ocean, they're actually quite a factor of 10 to the 4 less than the number of observations we have in the atmosphere. This is an example of a number of salinity data used on the 22nd of June 18 to compute the state of the ocean at the European Center, 500 coming from this observation, compared to the number of surface of conventional observation coming from CNOP, SHIP, and METAR of the atmosphere, 66,000. So you see that there is a factor 10 to the 4 to 10 to the 5th difference between how well we observe the ocean compared to how well we observe the atmosphere. The third reason, the third factor that makes weather forecast difficult and justify why we are using Ensemble is the fact that the atmosphere is chaotic. And we have error growth that depend very much on the flow in which we are. With situations like this one, when an ensemble of points starting close by stay close by for the whole time evolution of a system, while there are cases like this one or the third one, where even if you start, if you take initial points which are very close to each other at initial time, they start diverging very soon. And it's very difficult to predict where the system would be later on. So the fact that we have observation errors, or we don't observe the whole state of the atmosphere well, the fact that we have model approximations due to the fact that we are resolving the equations in an approximate way, and the fact that the atmosphere is chaotic causes forecast paths like this one. Cases when our forecast, day 5 forecast, which are usually very good. This is what I'm showing here, are the anomaly correlation coefficients of forecast from 5 centers. 100 means perfect forecast. So even if on average we are above 0.85%, which is a very good score, and there are cases when the forecast can get very wrong, okay? Now, it's very way to estimate forecast uncertainty. This is what people started working on in the 80s and the beginning of the 90s. Clearly, if you have one single forecast only, you know reality today, you launch your forecast, you don't know really where, this is an ensemble mean forecast, it's very hard to know whether reality, where it will end up. Will it end up close to this point or far? No, indeed, in some cases it might end up quite far, or in some cases quite close. If you had access to only one single forecast, it's very difficult to estimate your confidence around this forecast. So are there ways to do it? Yes, one way to do it, and the way that everyone has been doing it since 1992, when we put in operation the first ensembles at the European Center and in the US, we have been running ensemble of forecast. And we have been using information about the divergence of these ensembles as a measure of a confidence in our forecast. When we see that the ensembles stay close to each other, then we think, we say, okay, given if our ensemble is reliable, we could use the divergence between the forecasts as a predictor of how close the reality will be. So cases when the ensemble spread is small can signal cases where predictability is high, and we can make forecasts which are more accurate than on average. Okay, so I hope I've covered my second point, which is why do we need the ensembles? Now, how should we design the ensemble? Clearly, it's very important that one tries to simulate all the possible sources of errors. So I said that we have errors coming from a model, which also feed into the data assimilation. We could have errors coming from observations. We could have errors coming from the data assimilation procedures. Okay, so ideally, one should try to simulate all sources of forecast uncertainties. This is not easy, and indeed a lot of efforts and research has been put into trying to design the best method to do so. It's not easy because running, instead of one, many ensembles require computer power. And computer power clearly depends, as we said, from a model complexity and resolution, the number of members you can want to run, and the forecast length. So you can clearly see that there is a trade-off here. Given a certain amount of computer power, how should they use it? Should they run only one forecast with a very high resolution and a lot of processes up to only maybe 10 days? Or should they run an ensemble of forecasts, maybe at lower resolution, trying to include as many processes as possible, but possibly for longer than 10 days? Okay, so these choices, and then how should I design my ensembles? These are all choices that we had to make, because it's clear that we cannot run a very large number of members. And indeed, today everyone is running order between 10 and 100 members. Okay, so at this NWF, just briefly review how we have done it. We have decided to focus on trying to identify areas and patterns that could lead to large errors in the forecast. The way we have been identifying these structures, these perturbations at initial time, is by applying some linear technique and computing so-called singular vectors. So we need to solve an eigenvalue problem defined by the tangent forward and adjoint operator of a nonlinear model with some weights that define essentially how you want to, what type of statistics you want to enforce at initial time and at final time. We have also been using, following the example of what has been done in Canada since 1995, an ensemble of data assimilation. So an ensemble of initial conditions and computing differences between them. Define a new set of perturbations, which are quite different from the singular vectors that you see here, which are quite localized in space. EDA-based perturbations are sensitive to observation errors, have a much smaller scale. They cover the whole atmosphere. And by combining these two set of perturbations, we have been able to sample in a more realistic way the initial error, and also to build ensembles which are more reliable. Ensembles for which there is a much better correspondence between forecast probabilities and observed frequencies. But as I said before, this is essentially what we've done to simulate initial conditions. What about model uncertainty? As I said before, no, the atmosphere energy spectra is a continuous. We make choices on the model resolution, so we introduce an artificial truncation in our models. We are not simulating this case below our truncation. And one of the questions that we have to ask ourselves is, how can we possibly simulate the effect of SKEs which are not in the model on the SKEs that are on the model, for example. Second point, we are trying to simulate complex processes like this convection in the tropics by representing the average state of a system in a big box like this one. Possibly maybe even on a smaller box, but still you can see that the details of the structure of a cloud cannot really be simulated well inside the model. And then let me remind again that even a model with a 9-kilometer resolution has an actual resolution which is about 5 times that. So how can we resolve the effect of these small scales, the resolve scales, on the shorter scales simulated in the model so that we can have a more accurate simulation of a phenomena we are more interested in, like synoptic scales in the exotropics, organized convection in the tropics, and so on. Well, we have thought that the way to do that was to introduce in our models an extra term on the right-hand side that would simulate the effect of this error, of a model error, by using stochastic methods. In particular, since the end of the 1990s, we've been adding 2 types of stochastic models. What is called a stochastically perturbed parameterized tendency system, which perturb the full tendency using random perturbations with a certain spatial and temporal characteristics. Furthermore, we have also added what is called a stochastic kinetic energy backscatter scheme to try to simulate the effect of the unresolved scales on the resolved scales. The SPPT scheme acts on 3 scales to try to take into account errors happening over a fast and small scales and over a long and slow scale. And the backscatter scheme tries to compute the energy that the model dissipates due to processes, due to parameterizations, and reinject part of it, so as a ratio of it into the large scale, into, in this case, we were injecting it into the stream function with a certain pattern that we wanted to enforce. Okay, so the effect of all this work has been that today, as I'm speaking, ECNWF is almost all, or say the most part of the products generated by the European Center are based on ensembles. If you think about the analysis problem, there is still a single high resolution analysis. Then this analysis uses a 51-member ensemble of data assimilation to compute flow-dependent statistics, and the ocean state is computed using a 5-member ensemble. These two systems take into account observation uncertainties by perturbing the ops, and the ADA also model uncertainty. We go in forecast mode. ECNWF is still running a high resolution model up to 10 days, but then all the rest of the forecasts are done using ensembles, a 51-member medium range, 51-member monthly, and a 51-member seasonal system. All these have been designed, first of all, to have a coupled ocean, a coupled sea ice system. They simulate the initial uncertainties using a combination of signal vectors and EDA-based perturbation, EDA-based perturbation that are sensitive to observation errors, and model uncertainty schemes. I mentioned the 2, SPPT and SKEB. Okay, so what about climate? A couple of words about climate studies using Earth system ensembles. There as well, the community has realized since many years ago that it doesn't really make sense to try to make a climate projection using a single integration only. And since about 20 years or so, they have also been running these forecast scenarios using an ensemble of trajectories. Ensembles often generated by using multimodal approaches, whereby they combine single integration generated by different groups using different models. I want to focus more on something that has been done at the European Centre, which was to try to improve our estimate of the past climate, of the climate of the past 100 years since 1900, using an ensemble of coupled climate reanalysis. So here you see all what we have discussed so far, the use of an ensemble method, the use of Earth system to try to improve our simulation of a state of a system in the past. This so-called CERA system, coupled SNWF reanalysis data simulation system, have been simulating observation uncertainties by perturbing the ops, model uncertainties by stochastically perturbing the model, and also have been simulating some forcing uncertainties by taking into account uncertainty in the forcing as well. Okay, the scheme is under now testing to be used also in operations. SNWF plans in the next couple of years or so to move from an uncoupled type of analysis system, whereby the atmosphere, land, waves, and oceans are only very weakly coupled or uncoupled, to a system where coupling is increased, like using this type of coupled data simulation, which was established for this to generate this CERA 20C reanalysis. Has it been valuable to have an ensemble of reanalysis instead of only one? Yes, very much so. Here I'm showing you why has it been valuable? Because it has allowed us to estimate the uncertainty on our estimate of a state of a system in the past. What you see here is an example of this. This is the mean sea level pressure. The ensemble mean of a 10 analysis in black, the spread with these arrows. What you see is that after the 50s, when we started having more and more accurate observations of the state of a system, the spread among the couple reanalysis has been lower. So there is less uncertainties in our knowledge of a state of a climate up to 1950 than before that. And I think this is a very relevant information if we want, for example, to try to understand how climate has been varying. We need to take into account the uncertainty in our estimations when we make consideration of whether the climate has been warming or not. And here is another example, which is the spread of this analysis, of this 10-member analysis throughout the years, starting from 1900 to 2000. As you can see, this is in terms of it's mean sea level pressure. It's a graph produced by Eric de Boissesson, who has written a nice report discussing this. So what you see is that while at the beginning, because we had much fewer observations, the analysis, the spread was in the orange and the red area. Then as the years progressed, there has been more convergence among the different analysis, and today the analysis produced for 2000 were much closer with values in the blue range than before. Let me finish with giving you a couple of closing remarks. So let me go back to the 3 questions that I posed at the start of my seminar. Why do we need Earth system models? Why do we need ensembles? And why do we need ensembles over system models? I hope I've convinced you that if we want to reduce forecast error and further extend the forecast kill horizon, we need to include all the relevant processes in our models. Similarly, ideally, we would like also to have a coupled Earth system data assimilation system. With this, I don't want to say that the forecast kill horizon is not finite. There is clearly a finite limit up to which we can predict scales. But we know, since work done in the past few years, also by myself with my colleagues at the European Center, that skill is scale dependent, and that the skill can be extended further if we are able to slow down the error growth rate. If we are able to improve our models and include relevant processes, I think we can still achieve a slower error growth rate, and so manage to keep pushing the forecast skill limit further into the future, especially for the large scale. Ensembles, why do we need them? Well, I thought I've shown you that if you had an information of a whole PDF of forecast state, it's much better than if you had only a single forecast. But I stress the fact that you need to have a reliable system to be able to do so. And to do that, you need to really think hard about how you simulate all the sources of forecast error. And this is my point number, my answer to the third question, which is you need really to try to simulate all the relevant process in these ensembles. Looking into the future, I think the centers and not just the European Center will be moving further into having a fully coupled Earth system model, where, for example, the cryosphere is much better simulated, the chemistry, or at least some simple chemistry, is simulated in a dynamical way into the system, and where, for example, the water balance, the fresh water balance, is fully closed in our system. Does it really matter to keep coupling? This is another example from of forecast run from using the CERA system in a period in the satellite era. The results from Patrick Laloyot, Per Dahlgren, and Dinan Shepard, who showed that if you have a coupled model run from a coupled initial condition, you can do much better than if you have an uncoupled forecast started from an uncoupled initial condition. The black curves are all above the zero line to suggest this. Furthermore, if you have a coupled DA, you can use information, for example, from the atmosphere. And these are results from Giovanna De Chiara and Christian Mogelsen. You can use data from the surface of the ocean or from the atmosphere to estimate the state of the ocean. This is the impact of assimilating scatterometer data on the state, in this case, the potential temperature of the ocean. As you can see, if you have a good coupled data assimilation system, you can propagate the signal coming from the atmosphere and the ocean surface into the ocean, the deep ocean. And with this, I thank you very much, everyone, for your attention. I'm happy to take questions. So I give the floor back to Gabriele, and thank you again, Gabriele, for inviting me